Okay, team, let's keep going. Now we're going to get to kind of the point of all of this stuff with the curl. We're going to talk about something that's really important to understand in physics and electrodynamics, which is the electric potential. Okay, so the point of this lecture, which will probably end up being a little bit longer, is to be able to describe how the electric potential is related to the electric field. All right, so let's get started. Previously, we argued, or I argued, I guess, or the book, or people in general, physicists, that the line integral of the electric field is independent of path. Okay. And again, this is based on the fact that the electric force is a conservative force. This is, by the way, not a closed integral, so it doesn't necessarily have to be zero. So what this means is that it doesn't matter how we do the integral or what path we choose. We get the same answer. And really, it just depends on the endpoints, okay? So these endpoints are pretty important. But we haven't really said what those endpoints are. I can look at this integral and tell you what the units should be. If you remember, this has units of newtons over coulombs, and this is going to have units of meters. So whatever this endpoint is, it's going to have units of newtons times meters over coulombs. Interesting. All right, let's call the endpoints of this integral potential. In fact, let's not just call it potential. Let's call it electric potential. Okay, electric potential, we're going to use the big V. All right, it's hard to tell sometimes in these lectures what's going on here. This is a big V for potential. And if I'm going to do this line integral from the limits b to a, then I'm going to end up with this potential thing evaluated at b minus that potential evaluated at a. Turns out we throw a negative sign in there. That's how we've defined potential. And that's going to be equal to our path independent line integral here. Okay, and I want to point out this negative sign especially because it's easy to forget. And I really think it's there because of the way we define potential when we think about it. We often make analogies with gravity. And that doesn't mean the original people that derived these laws were doing that. Okay, let's do this for a point charge. So let's just get an actual electric field in there and do this line integral. I'm going to do it between two distances, RA and RB. And this DL, this line integral, I can rewrite this as in spherical coordinates as R hat plus R d theta, theta hat plus R sine theta, phi hat. Okay, so this you can get in the back of the book, but basically what it's doing, again, you could derive it carefully, but it's all of this trig. It's turning a change in angle. So say I went 1 degree in theta. Well, DL is a distance. Okay, so I need to actually convert that to a actual distance traveled. So I can't really integrate over, do a line integral over, right, just an angle. I have to do a line integral over a distance. So r d theta represents the amount of distance traveled when I travel over a small amount of degrees in the theta direction. All right, so we're going to substitute in that spherical bit for our dl. In this case, our electric field only depends on r hat, so all of these other terms are going to go away when we take the dot products. That's going to simplify things. So I'm going to end up with just, let me do that negative sign. Like I said, easy to forget. Negative 1 over 4 pi epsilon naught r, actually I'm going to do the q out here too, rb ra 1 over r squared dr. And again, I ended up getting here, let me just write this out, r hat dot r hat, but that is equal to 1. So you can keep that in your notes if you want. I'm going to get rid of it just for space. Okay, but that's what happened with the dot product. Okay, when I actually do this integral, I end up with 1 over 4 pi epsilon naught q over r, and I have to evaluate that between rb and ra, so I'm going to end up getting 1 over 4 pi epsilon naught q over rb minus 1 over 4 pi epsilon naught q over ra, and this is the term that we would define to be the potential at a radius b, and this would be the term that we define to be the potential at the radius a. And as long as these r's are different, then these two potentials would also be different. All right, let's use a little bit more mathy math here to think about this further. So I'm not going to do a whole lecture on the fundamental theorem of gradients because it's a lot like our other fundamental theorems, in that you've got some kind of integral of a derivative being related to values at the endpoints. Okay, but the fundamental theorem for gradients would say that our difference in these potentials at our endpoints, let's just call them b and a now, would be equal to the gradient of our scalar field v. Okay, this has to be a scalar. And these are also scalars, by the way. Dotted with dl. Okay, so one way to think about this is that the difference in value at the endpoints here, okay, is the same as summing little steps and a path. Okay, so if I were to summarize this theorem, the difference in value at the endpoint, which is the left-hand side, this guy, is the same as summing, which is their integral, little steps along a path. Okay, so if you guys remember, let me just write this out first. So here's our little steps. The dv dx, that's the slope, and then if I actually multiply it by this, we just end up getting, right, little dv's, but we can change now, the scalar field can change in multiple directions. Running out of room here. Okay, so the book talked about in the fundamental theorem for calculus how this would be, right, like summing up the individual steps and having that be equal to the difference in height at the endpoints. This is also kind of like that, but that was kind of a one-dimensional view. This is a multi-dimensional view. So I think of it a little bit more like a drunken walk up a hill. You can kind of go straight up it, but a little bit to the side and around, rather than just taking the stairs straight up. Okay, but the same thing, all of that little path times all the little gradients is going to be equal to the difference in value at the endpoints. All right, let's use this guy to do something that has to do with electric fields. So I'm going to write it out again. All right. We said before, the whole reason for defining this electric potential is to have some thing that this particular line integral can be equal to. We know it depends on the values of the endpoints, but we hadn't actually said what those values at the endpoints are. Okay, so if this is equal to this according to the fundamental theorem of gradients, then this is also equal to this, and therefore this, the integrand, must be equal to that. So I can write now that, we'll do one of these, therefore the gradient of V, which is our potential, is equal to the negative of the electric field, or more commonly written as the electric field is equal to the negative of the gradient of our potential. Okay, I want you to think about this in terms of that PhET sim that I just showed you. Remember where the equipotential lines were indicating that the potential was changing at a faster rate? We got a stronger electric field. Well, that is in agreement with this particular definition. If the scalar potential is changing rapidly, then we're going to get a big value for the gradient here. That's going to give us a big electric field. If it's changing gradually, we're going to get a small value over here. That's going to give us a small electric field. Also, if you remember this gradient, the normal vector of it, or the direction that it always points kind of straight downhill. That's the one way you want to think about it, or in the direction of the greatest change in the potential. That's always going to be in the direction that is perpendicular to equipotential lines, which is in agreement with the fact that we observed that the electric field is always perpendicular to equipotential lines. Okay, so we've got this cool thing now called a potential, which is relating a scalar field. This is scalar, so just like height or temperature or anything like that, to this thing that is a vector, which is the electric field. Okay, what turns the scalar into a vector is taking the gradient. If you remember this del operator, it turns our scalar fields into vector fields because our scalar fields can have rates of change in more than one direction. Okay, so this is cool. I like this. There is a scalar value. Okay, it's worth noting it's not like it's a single value. It's still multi-dimensional, which means it's still this thing that can change with X, Y, and Z. Okay, that can be used to define an electric field. Almost. We're not quite done. Okay, we're almost there. What we're missing is the fact that we haven't uniquely defined our electric field. Okay, why? Well, if the electric field is equal to the negative gradient of some scalar field, okay, then the electric field is also equal to the negative gradient of that scalar field plus a constant. So I could add some arbitrary voltage or potential to my scalar field, and I would still calculate the same electric field. So essentially, the problem here is more than 1 can correspond to the same electric field. Okay, that's not really a problem, but there's a way that we can solve it. And the way that we can solve it is by actually setting what the voltage should be at some particular boundary. Okay, so our solution, if this is our problem, then our solution, getting a little messy here, is to specify a value of V somewhere. Okay, so what's typical in the limit as r goes to infinity, we say V sub r goes to 0, okay? Which is essentially like saying that when you get really far away from a point charge or a charged disk or a charged ring, the E field goes to 0 at infinity. So if this is true, then we can write something like this. If I take the integral of the electric field from r to infinity, okay, that's going to be equal to the potential at that position r minus the potential at infinity. If I allow this one to go to 0, then I can say that the electric potential is equal to, for example, 1 over 4 pi epsilon naught Q over R for a point charge. So this means that I can calculate some potential around a point charge by putting in Q and R and epsilon naught, and it's not arbitrary. It is unique for that particular point charge. Okay, and this is related to something called Helmholtz theorem, which I'm not going to go over in too much detail right now, but basically that says that a field can be uniquely determined by its divergence and curl, okay, as long as boundary conditions are applied, okay? And we are here now because, right, we have specified what the curl should be of the electric field. We have specified what the divergence should be of the electric field. And now we have boundary conditions, okay? All right, so let's go ahead and summarize. This potential, what we call electric potential, is a scalar field, which means it doesn't have any, in an individual point, you just have a value. It's not a vector, okay? That's important to remember. We have this equation for the potential around a point charge. Where here I'm going to write it in terms of a separation field, which basically allows that point charge to be, or the separation vector, which means the point charge can be anywhere. Well, instead of saying anywhere, I'm going to say the position vector of the point charge doesn't have to equal 0. That's what that allows me to do, okay, but I have an equation for it. But this equation, it's important to remember, it defines the potential at point R for a point charge, not for any charge, not for any charge distribution, just for a point charge at point r prime. Okay, but it is also assumes that v sub r equals 0 at infinity. Okay, which in some cases it doesn't make to assume that. If you've got a, for example, sheet of charge or a line of charge that goes all the way to infinity, you actually get in trouble when you assume the potential is 0 at infinity because you have charge there. Okay, but that's a special situation. Okay, the book also brings up, and I talked about in the PhET sim, we've got these things called equipotential lines. It's important to understand what that means. Or lines or regions or whatever of constant potential. And the last thing we didn't really talk about explicitly are the units of potential, which are 1 Newton meter over Coulomb. Turns out that's the same as 1 joule over Coulomb because work units are Newton meters. Work is the same thing as energy. Energy units are joules. Okay, and 1 joule Coulomb, 1 joule per Coulomb is the same thing as 1 volt. Okay, so the volt is the most commonly used unit for potential, but all of these other units work too. And of course, you can break down this compound unit even more into like things like kilograms and meters and seconds if you wanted to break out that newtons.